All right, welcome back. We're now in section 2. So we're going to start to get ready to do some calculations here. And before we can do that, we need to spend a little bit of time talking about gas pressure. We've talked a lot about different types of measurements that we're going to be using in this topic about gases. We've talked about volume, we've talked about moles, we've talked about temperature, but we really haven't spent any time talking about pressure, or at least very minimal time. We've only introduced it, but we haven't really spent some time on that. So let's go ahead and do that now. So first of all, let's talk about what pressure is. What is it defined as? Pressure is defined as force per area. And even that we need to break down a little bit. If you've never taken physics, you may have never heard of, or at least studied force. You've probably heard of it, but you don't really know maybe what a force is. Really easy to remember, a force is simply a push or a pull. Anytime you push or pull something, you're applying a force. Well, in terms of gases, we're going to talk about the push. So over here is a container of gases, and normally if the PowerPoint was running, it would actually show the particles moving around. It's an animation, but imagine they're moving around, and gas particles are moving all over the place according to the kinetic molecular theory. Well, what they do is they move in straight line motion, and then when they hit the sides of the container, they're going to bounce off. Well, every time they hit the sides of the container, they're exerting a push. And we measure force, or pushes, in units of newtons, which is a capital N. Now, that force, or that push, is applied over a very, very, very small portion of the container. And that small portion is the area. And the SI unit for area is meters squared, because, the length is just a meter, so meters squared would be area. And so if you think about a certain amount of push, or force, over a certain area, meters squared, this is where you actually get pressure. So pressure comes from exerting a force over a certain area. Now, we don't want to have to write newtons per meter squared all the time, and so we actually came up with a unit that encompasses that, and that's known as the unit of Pascal. Now, normally, we're dealing with very large amounts of pressure, so you're probably not going to see Pascal as much as you see the metric version, kilopascal. So you'll see that a lot more. And 1 kilopascal is 1,000 pascals. But nevertheless, that's the unit of pressure. Now I want you to think about one gas particle. It's very tiny, hitting the side of the container. One gas particle itself does not exert a lot of pressure. In fact, it barely exerts any pressure at all. But if you think about a lot of gas particles, and we're talking a lot, like a lot, and they're all doing the same thing. They're all hitting the sides of the container at various times. Collectively, gas particles exert quite a bit of pressure. Think about it. I want you to think about, I'm going to try to draw a car. It's going to be terrible. Actually, it's not too bad. Actually, I did pretty good. Pretty proud of myself for that. Okay, you think about a car. Car weighs a lot, right? What's holding up your car? The only thing that's holding up your car is the tires. Well, what fills your tires? It's air, right? It's gas particles. Gas particles are effectively what is holding up your heavy car. So collectively, gas particles exert a heck of a lot of pressure, and they can do amazing things depending on what their conditions are. When you think about gas particles moving around, like we talked about in the previous video with kinetic molecular theory, they are always going to exert pressure on everything they touch. Every time a gas particle touches something, it exerts a pressure. Now, if you think about like a balloon, right? You've got the gas particles that are on the inside of the balloon, and they're what's hitting the side of the container and then bouncing back. That's what's known as your internal pressure, and we'll talk about that throughout the topic. But then you also have gas particles that are surrounding the balloon, okay? This is your external pressure, or a lot of times we say that it's the atmospheric pressure. Now think about it. If I were to just get rid of all the particles that were in this balloon, okay, magically I snap my fingers and all those particles, all those gas particles disappeared, what would end up happening? Well, the outside or external particles would end up just crushing the balloon, right? It would, kind of implode it a little bit. But if I did it the other way, let's say I got rid of all of these gas particles out here. There was no more external pressure. Well, these particles then would end up just expanding the balloon out more and more until finally the balloon would probably pop. So it's this balance, if you will, or it's this equilibrium of gas particles, both inside and outside, that keep a container at a certain condition, at least for a while. Now, as time goes on, gas particles start to slow down, gas particles leak out of the material, things like that. So like, for example, if you just left a balloon, let's say you had a birthday party, you leave the balloon, after a few days, you're going to notice the balloon starts to get a little smaller. And that's a combination of two things. One, the gas particles inside start to lose energy, and also some of the gas particles may escape the actual balloon itself. Not many, relatively speaking, but that's what starts to happen. Now, how do you measure atmospheric pressure? And how do you think about atmospheric pressure? Well, the atmosphere is made up of all kinds of gas particles, and we've actually mentioned some of them. Oxygen, of course, but oxygen actually is not the most abundant gas in our atmosphere. That would be nitrogen. But you got oxygen and nitrogen and argon and carbon dioxide and greenhouse gases and all kinds of gases that make up our atmosphere. Well, there's a higher concentration of gas particles towards the surface of the Earth. So if you think about like a column of air above, starting at the surface of the Earth and going straight up, kind of demonstrated here, you're going to find most gas particles are towards the Earth. And that's simply due to gravity. Gravity acts on everything that has mass, even tiny particles. So it pulls those particles down towards the surface of the Earth. And so that's why, just to kind of apply this a little bit, that's why airplanes travel at very high altitudes. Because if you think about an airplane trying to travel through, a lot of gas particles near the surface of the Earth, that gets very turbulent. If they fly up higher, there's less air particles to, make the plane shake. And that's why airplanes, when they're taking off as well as landing, kind of get a little bumpy because they're moving through all these particles. Also, a little bit of information, this is why in Arizona, especially when it gets really hot, sometimes the airport closes down in the heat, the dead heat of summer. And the reason why is because when airplanes are trying to take off and land, when it's really, really hot out, these gas particles, not only are there a lot, but they're moving very fast. And if they're moving fast enough, that can actually be detrimental to a plane. So, a little bit of tidbit of information. So that's a little bit about pressure. Now, how are we going to calculate with pressure? We need to be familiar with the units and how to convert from one unit to another. Probably the most abundant unit you're going to see, at least in this course for pressure, is the unit of ATM or atmosphere. So 1 ATM or 1 atmosphere is your standard pressure. If you were to think about what's standard pressure, what's the pressure of a typical room that we're in, it's essentially 1 atmosphere of pressure. And so like I said, the ATM unit or atmosphere unit is going to be the most abundant that we'll see. But sometimes the problem we're looking at has different units. So you need to know how to convert. And just FYI, all of these conversions are on the back of your periodic table, and so you can take a look at those. So first of all, torr and millimeters of mercury, you'll notice, have the exact same conversion. For every 1 atmosphere, it's equal to 760. And so I want to point out a couple things. Number one, notice they are the same thing. So for example, if I asked you to convert 680 torr to millimeters of mercury, it's literally the same thing. There's 680 millimeters of mercury because it's the exact same unit. The other thing is, note that these two conversions are exact. There's exactly 760 torr or 760 millimeters of mercury in 1 atmosphere. And so when you are figuring out what your sig figs are for a problem, remember it's not going to be based off of these two because they're exact conversions. Another one you might want to be familiar with is the Pascal. There's 101,325 pascals, or that could also be 101.325 kilopascals in 1 atmosphere. Now this one's not exact, and so if you're going to use this conversion, please note that this will dictate sig figs. And then finally, PSI, pounds per square inch. You may have heard of that one before. That is also equal approximately to 1 atmosphere. This as well is not exact, so significant figures will definitely play a factor with these two. So let's do some real quick conversions just so we can feel comfortable on how to do these. So the very first one, we want to convert 1.613 atmospheres to kilopascals. So I know that 1 atmosphere is equal to 101.325 kilopascals. And I'm not going to calculate the answers here because that's the setup, and hopefully you'll know how to calculate that. But that would be your setup. For number 2, 732 millimeters of mercury to torr. Well, remember, these two units are the exact same. So if it's 732 millimeters of mercury, it is 732 torr. There's really no conversion there. Now, this last one is kind of a couple, right? So we have 860 millimeters of mercury, and we want to convert to 2 units, centimeters of mercury, and then inches of mercury. We're going to get into, on the next slide, how we actually used to measure air pressure. But a little spoiler alert, we used to use mercury back before we realized how toxic it was. And so the unit of millimeters of mercury actually came from just measuring the height of mercury in a column. And so that's how we got the unit of millimeters of mercury. So it doesn't really matter that it's mercury, okay? So I could cross that off just temporarily. We're really just looking at how to convert from millimeters to centimeters to inches. And that's hopefully something you remember how to do. So first I want to calculate or convert 860 millimeters of mercury into centimeters. Okay, so millimeters of mercury on the bottom, centimeters of mercury on the top. Ignore the fact that it's mercury. Just think millimeters to centimeters, right? Well, the centimeter is the larger unit of the two. So for every 1 centimeter, there are 10 millimeters. And so that'll cancel out that. And then to go from centimeters of mercury to inches of mercury, once again, ignore mercury. Just think centimeters to inches. For every 1 inch, there are 2.54 centimeters. And so that'll cancel out my centimeters of mercury. And that's how you would convert into inches of mercury. Which, by the way, if you have the weather app on the iPhone, I'm not sure about the Android, but the iPhone, if you looked up weather and you scroll down and you were finding pressure, this is actually the unit that they report atmospheric pressure in, inches of mercury. So, little tidbit. All right, we're almost done with the video. The last couple slides just talk about how we measure pressure. If you want to measure atmospheric pressure, we use what's called a barometer. Now, most of our barometers today are either digital or they use a different liquid, but old school barometers, they used to use mercury. And real simple, what it was it was a basin of mercury, and there was an inverted tube that had a vacuum. So remember, there's no gas particles up here. And this tube was marked, and specifically it was marked with millimeters. And essentially what they did is they said, okay, well, if the atmospheric pressure was high, that would mean that the particles that were in the atmosphere around would be moving. There would be a lot of them, and they'd be moving around, and they would make collisions with the surface of the liquid and then bounce off. So this particle would come and bounce off, and so on and so forth. And if there were a lot of particles doing that, there would be more collisions down here at the surface of the liquid. Well, if there's more collisions pushing on the surface of that liquid, more demonstratively over here, then that would cause the liquid to rise up higher in the tube. And so that's how we used to measure atmospheric pressure. And that's also where we got the unit of millimeters of mercury. Another way to measure pressure for a gas is a manometer. And so manometers are ways that we can measure pressures of gases other than atmospheric pressure. Specifically, maybe you're doing an experiment and you're trapping a gas inside a particular vessel, and you want to be able to measure what the pressure is. So to do that, there's actually 2 types of manometers. There's closed manometers and open manometers. In a closed manometer, the tube here is sealed, so it's closed. So there's a vacuum right here, so there's no air here. So the pressure of the gas inside the bulb here is simply just going to be the difference in height. And so these tubes would actually be marked. Okay, they would be marked with, measurements. And whatever those markings were, whatever that difference in height was, that would be your pressure. And so if the height difference was 50 millimeters of mercury, then that was actually the pressure of gas in there. So closed manometers are very straightforward. An open manometer, which actually is a lot more common, is a little bit different. So an open manometer is one in which the tube is open. So not only do you have the gas of pressure of the gas in the tube, but you also have the pressure of the atmosphere. So this gas here it's filling the tube and it's pushing down on the liquid here. But the pressure of the gas in the room, the atmospheric pressure, is also coming in and pushing down. So there's like this push-a-war. Okay? So to figure out what the pressure is of the gas, you have to first take the difference in height. So let's say the difference in height was 50. But then you have to either add it or subtract it to the atmospheric pressure. So if I were to take a look at this, it looks like the atmospheric pressure is higher because it's pushing the liquid level down. How much higher? 50. So the pressure in the bowl would be 7